Welcome to the lecture 4 of our course, Introduction to Complex and Algebraic Geometry. Today we are going to learn about Poincare dbar Lemma. This is one of the most essential facts in complex analysis and complex geometry. Before starting to discuss Poincare dbar Lemma, let's do a quick review about the things we previously learned. We learned two essential things. We learned about holomorphic functions. So holomorphic functions defined on C. We learned they're essentially the same as complex differentiable functions, and they are essentially the same as analytic functions on C or on domains inside C. And the second thing we learned was Cauchy's integral formula. Cauchy's integral formula. Right. Now, today we're going to learn about dbar lemma. And actually, it is very much connected to the things we learned up to this point. It's kind of an application of Cauchy's integral formula. Before telling you what dbar lemma is, let me remind you of a simple fact from calculus of real functions. Suppose we have a real function, let's say smooth integrable function g from R to R. So a real valued function, just like the functions we used to study in calculus. The domain is R. R is an interval inside R. Maybe it's not defined everywhere in R. Maybe the domain is a smaller subset. Anyways, let's say I'm looking for a function. So I'm looking for a function f, also defined on R, or again, a subset of R, so that the derivative of f at every point x is equal to g, right? So G is given. So G is given. And let's say there is a question that wants me to find F. So F is the unknown, right? This is essentially a differential equation, ordinary differential equation. I don't have F, but I have derivative of F. I know derivative of F is equal to G. So what is F? It's not very hard to guess what is the function F, right? We have derivative of f. In order to get what f is, we should apply antiderivative, or essentially integral, right? So f of x would be given by integral of g. Let's introduce a new variable t. Um, we should fix some base point, let's say 0 up to x, right? This would be the formula for f. I'm sure you remember from your calculus, there's always a constant plus c, right? So if I take derivative of f, I would get g, right? This is pretty straightforward. And it's also quite important that we have here plus a constant c. So this means this equation has a solution, and the solution is unique up to addition by a constant, right? We found a solution in terms of g. So this integral is a formula in terms of g. So we had the equation and we solved it. And it's pretty simple and straightforward. Now there is a similar thing in complex analysis. So over reals, we can take derivative of f with respect to x, right? Which is essentially derivative of f with respect to x. In complex analysis, when I have a function f defined on C or a subset of C, we introduce two forms of derivative. We introduced derivative of f with respect to z, partial f partial z, and we introduced derivative of f with respect to z bar. Remember, they had their own definition. So what was the definition of derivative of f with respect to z? It was 1 over 2 derivative of f with respect to x minus I derivative of f with respect to y. And what was the definition of derivative of f with respect to z bar? It was 1 over 2 derivative of f with respect to x plus I derivative of f with respect to y. So we kind of discussed this why these are the why there are natural definitions for the derivative. We will discuss them again when we get to the notion of complex differential forms. But at this point, you can kind of take them as definition, right? So we have these two derivatives with respect to z and z bar. Now, what is the analogous of the theorem we saw earlier? So this would be the question. Suppose a function g is given either on C, so it's either a function from C to C, or it's given on a subset of C. So maybe U is a domain inside C, let's say a bounded domain, and then we have the function g to C. Let's assume the function g is smooth, let's say it's bounded, let's say it even has bounded extension to the boundary of U, so it would be integrable, all the good things. And then we are looking for another function, looking for a function f defined on this region, so that derivative of f with respect to z bar is equal to g. So derivative of f, we could look at derivative with respect to z or z bar. Let's do z bar here, equals g. So again, g is given, and the unknown of the equation is f. Can we solve this? Can we find a solution for this? Right? And if we trust our intuition from the real case, in the real case, f was given by an integral in terms of g, integral in terms of g. So the essential question is that, can we do the same thing here? Can we define some integral in this complex case, where it would give a formula for f in terms of g that would satisfy this equation, right? Can we do that? Can we find such f? Look at this equation for a few seconds. Feel free to pause and look and see if you can guess, if your knowledge from calculus can help you to guess what the formula for f should be. Okay, so this is the equation. Derivative of f with respect to z bar is equal to g. So there are two questions, just like the real case. One is the question of existence of solution. Is there any solution f? And then the other question is, just like the real case, is the uniqueness of solution. Is there just one solution? So in the real case, we learned it's unique up to addition by a constant. What about what is the uniqueness theorem here? So before answering the existence theorem, which is slightly more complicated, let me try to answer the uniqueness. Okay. So what does uniqueness means? It means suppose you already have a solution. So suppose we could find some function f so that its derivative with respect to z bar is equal to g. Is there any other function f so that its derivative with respect to z bar is also equal to g? The way to answer this question is that suppose there is also another solution, let's say f tilde, so that its derivative with respect to z bar is equal to g. So in other words, suppose there are two solutions. What can we say about f and f tilde? It may be like the real case, f tilde is f plus a constant, like just the plus c coming out of the integral, maybe something like that is correct. So we should see that. You know, the point is that as soon as we have this equation, it means these two terms are equal, right? So I have derivative of f with respect to z bar is equal to derivative of f tilde with respect to z bar. I can move both of them to the left side of the equation. So derivative with respect to z bar of f minus f tilde is equal to 0. Now, we had this simple theorem or lemma that a function satisfies the Cauchy-Riemann equations or is holomorphic. So a function is holomorphic. A function, let's denote a function h is holomorphic if and only if derivative of h with respect to z bar is equal to 0. So we learned this is another way of writing Cauchy-Riemann equations, right? So if f minus f tilde has derivative with respect to z bar equal to 0, it means F minus F tilde is holomorphic, right? So let's denote the difference with H. So if we find one solution to the equation, any other solution is equal to the solution we found plus a holomorphic function, right? Holomorphic function H. So the solution to the equation is unique up to addition by a holomorphic function rather than by addition with a constant. So the equation derivative of f with respect to z bar equals g. If it has a solution, the solution is unique up to addition with a holomorphic function. Okay. Because if I add the holomorphic function h, derivative of h with respect to z bar would vanish, so it doesn't affect the equation. Now that we addressed the uniqueness question, let's go back to the existence question. So is there f, is there a function f so that derivative of f with respect to z bar is equal to g? So here we are assuming G is defined on some open subset, some domain U, which is bounded, right? Let's fix this case, this setup. You see, on the left-hand side of the equation, I see derivative of f with respect to z bar. Do you remember any formula which has derivative of f with respect to z bar in it? So the formula that includes such a term is Cauchy's integral formula, right? Remember, for any function f, which has some smoothness properties, Cauchy's integral formula tells us that the value of f at any point is given by an integral on the boundary of u, where the integral is f of z over z minus z naught dz, plus a second term that would exist if f is not holomorphic. So the second integral was over an integral over the whole u, which includes derivative of f with respect to z bar, dz, dz bar over z minus z naught, right? So this is good because now we see this term we were looking for. This formula relates the values of f at some points with its derivative with respect to z bar. So if we find some solution, this term here is supposed to be equal to g of z, right? Okay, so this is equal to, if f is a solution to the equation, this would be equal to this integral on the boundary plus 1 over 2 pi I integral over u g of z dz dz bar over z minus z naught, right? This is good because this kind of tells us what f should be in terms of g. Note that this integral only includes g, no f. However, this doesn't exactly work. Why? Well, the bad thing is that there is another integral here. This is the bad integral because it still includes f. We cannot isolate f. If for some reason this integral would vanish, so if there was a reason that we could get rid of this integral, then we could isolate f. F was given by a formula that only contains g. That would have been the answer. That would have been f written as an integral in g. That would have been great. So what can we do about this first term? So this might kind of sound weird. Um, we are looking for a function f to solve this equation. Rather than looking among all functions, like I'm looking for a function f that would satisfy this equation. Rather than looking among all functions f from u to c, I kind of restrict the set of functions I'm considering. This might sound bad, but I only look at the functions. I only look for f among functions that they vanish on the boundary of u, that f is equal to zero on boundary of u. So I just look for the functions that on this boundary of u are equal to zero. So this might sound bad because if I'm looking for something, if I look in a larger set, there's a better chance of finding the thing I'm looking for rather than looking in a smaller set. However, this would be very beneficial. If I look only among functions that they vanish on the boundary, what would happen is that the first integral would vanish because f would be equal to zero on this region I'm integrating, right? F would be equal to zero on the boundary. So this term would completely disappear, right? So among the functions that vanish on the boundary, if I'm just looking among them, they still would satisfy the Cauchy's integral formula. However, because they vanish on the boundary, they would not have this first term. And then this gives me a formula, right? So if f satisfies derivative of f with respect to z bar equals g, and if f is equal to zero on boundary of u, then f of z naught at every point z naught is given by this formula, right? But the question is that it's kind of the other way around. I should prove there is a function f that satisfies this equation. I'm saying if there is a function f satisfying this equation and zero on the boundary, then that function is given by this formula. You see, this is kind of like doing reverse engineering. I want to solve this equation. If I can find any way to guess what the answer to this equation is, I'm good. Because if I guess correctly, then I can just bring that answer and plug that into the equation and see if that is a solution or not. You see, now I can say, well, let's try this. Try this one. I have a formula for f. I just define the function f by this formula, and I just plug that into this equation. So I have a definition for f. I just take its derivative with respect to z bar. And then I can see this is indeed equal to g. So this might look a bit weird. We kind of reversed engineer. We looked among smaller set of functions. We wrote the Cauchy's integral formula for them. And then we got an expression for f, that if f satisfies this equation and zero on the boundary, what should f be? And now, if I want to prove this as a theorem, I can say, okay, I want to prove this equation has a solution. I guess the solution looks like this. I only need to plug that into the equation and check its derivative with respect to z bar is equal to g. We are going to do that, and that would be a straightforward thing. So in the next part of this lecture, we are actually going to take derivative of this function with respect to z bar, and we are going to see this is equal to g. But before doing that, I want to discuss this a bit more, that why assuming f is zero on the boundary was not kind of a weird assumption. So we were trying to solve this equation, and suddenly I said rather than looking among all functions, let's just look among functions which are zero on the boundary. Why does it make sense? The point is that the reason why this really worked, philosophical reason why this worked, is that the claim is that if this equation has a solution, so if, let's denote it with star, if star has a solution, then star must have must have potentially another solution, potentially another solution. So has a solution f, it must have another solution f tilde. That f tilde is equal to zero on boundary. So if you find one solution, there must be a solution that would vanish on the boundary. Why is that? Why does it have to have a solution that vanishes on the boundary? This goes back to our uniqueness discussion. If this equation has a solution, f, remember, if I add any holomorphic functions, h to this, this would be another solution. So if the function f itself does not vanish on the boundary, I can always find a holomorphic function so that the value of f plus h would be zero on the boundary. So if f on boundary is has some values on the boundary of u, I can always pick a holomorphic function h, which the value of h on the boundary is exactly equal to minus value of f on the boundary. And this is, I leave this to you. I like you to think about it. Why you can always find a holomorphic function h so that the boundary value of f plus h, this new function f tilde, is equal to zero on the boundary. This is an application of Cauchy's integral formula. But now, just to prove it as a theorem, this was more like a way of guessing what the answer should be. So we were given an equation, so we were theorem. So G was given, G was a map from U to C. Let's say G is smooth. Let's say it has bounded extension to the boundary. We were considering the equation derivative of f with respect to z bar equals g. We were wondering if it has a solution or not. Everything we did helped us to guess what the solution must be. The equation derivative of f with respect to d bar equals g has a solution, and we know solution is unique up to addition with holomorphic curves given by the formula we learned. 1 over 2 pi I, derivative of gz, dz bar over z minus z naught, integral over u. You see, now that we guessed, we can prove it. But if we had no idea what the formula for f should be, there was no way to prove this. This is, well, there are ways, but this is a kind of more straightforward way of doing it. Well, we should prove this. Now that we have the statement, we try to prove this. What should be the idea of the proof? Well, now that we have a formula, we want to just take derivative of the formula we have, like we are plugging in our solution into the equation. We do computations. And the hope is that after applying computations, we would really get g of z. So if we do that, then we are done. That's what we want to do. And that's what we would be doing in the next part of this lecture.